Hello, higher physicists. Today we're going to have a look at the astronomy questions from the 2019 Higher Physics paper, paper 2, which is questions 4 through to 6. So let's get started. Question number 4. A communications satellite orbits the Earth at a height of 36 times 10 to the power 6 meters above the surface of the Earth. The mass of the Earth is 6 times 10 to the power 24 kilograms, and the radius of the Earth is 6.4 times 10 to the power 6 meters. A. Determine the distance between the center of the Earth and the satellite. So, as we can see in the diagram, the satellite orbiting at a height of 36 times 10 to the power 6 meters, that's above the surface of the Earth. So to find the distance that it orbits above the center of the Earth, we need to add on the radius of the Earth, which were given in the question there. So it's a straightforward adding up sum. 6.4 times 10 to the power 6 plus 36.0 times 10 to the power 6 gives us a total height of 42.4 times 10 to the power 6 meters. Part B. The gravitational force of attraction between the Earth and the satellite is 57 newtons. Calculate the mass of the satellite. So, for this we can use Newton's inverse square law of gravitation. F being the force of attraction between the Earth and the satellite, G being the gravitational constant, which we can find in our data sheet, M1 and M2 being the mass of the Earth and the mass of the satellite, and R being the radius of the satellite's orbit, what we found out in the previous question. So let's place our numbers into the formula, and we get, as you can see there, quite a bit of a fiddle for rearranging here. The first thing to do is to get the divided by 42.4 times 10 to the power 6 squared over to the other side. So we are going to multiply both sides by 42.4 times 10 to the power 6 squared. And that gets us to here. Now we want to take the gravitational constant and the mass of the Earth, the 6.67 times 10 to the minus 11 times 6 times 10 to the power 24, and move that to the other side. As we're multiplying by them on the left-hand side, we're going to divide the other side. And here we are. We end up with a value of 260 kilograms as the mass of the satellite. Part C. Determine the value of the Earth's gravitational field strength, G, at the satellite. So, gravitational field strength. Hopefully you'll remember from National 5 this formula, W equals mg, which stands for weight equals mass times gravitational field strength. Now, in the previous part of the question, it talked about the force of attraction between the Earth and the satellite. Now, the gravitational force of attraction and weight are the same thing. Okay? Weight is the gravitational force of attraction that holds you on Earth. Usually we think of weight being at the surface of the Earth, but the weight is the force of attraction wherever you are due to the gravitational field. So, we know the weight. The weight is that gravitational force of attraction, 57 newtons. We worked out the mass of the satellite in the previous question, 260 kilograms. So from that, we can work out the gravitational field strength, G. And we have a little bit of rearranging to do. And we get a value of G to be 0.22 newtons per kilogram. Part D. A second satellite has a quarter of the mass of the first satellite. The distance from the center of the Earth to the second satellite is half the distance from the center of the Earth to the first satellite. State how the gravitational force of attraction between the second satellite and the Earth compares to the gravitational force of attraction between the first satellite and the Earth. Justify your answer. Well, we can justify it qualitatively by saying the second satellite having a quarter of the mass means it would have less force acting on it, but because it's half the distance from the Earth, that would have more force acting on it. So there's two things at play here. The easiest way to figure out exactly what's happening is to just work it out. So we're going to use Newton's inverse square law of gravitation again. And this time we have these numbers. Now the mass, the second mass, is 0.25 times 260. We know the original mass of the satellite was 260. This one is a quarter of the mass, so 0.25 times 260 will give us a quarter of the mass. And the distance from the center of the Earth to the second satellite is halved. So I've put in as my distance a half, or 0.5 times 42.4 times 10 to the power 6. And then I just work it out. And I end up with a force of 57 newtons. Therefore, the force is the same. There is no change to the force. It's important in this question, by the way, if you do work it out, that you also make that final statement, because the question says, state how the gravitational force of attraction compares. If you don't make that final statement, that there's no change to the force, then you cannot get all of the marks, even if you have correctly justified it. The statement is still required. Number 5. A person is standing at the side of the road. A car travels along the road towards the person at a constant speed of 12 meters per second. The car emits a sound of frequency 510 hertz. The person observes that the frequency of the sound heard changes as the car passes. State the name given to this effect. Well, this is called the Doppler effect. Part B, or part A2 rather. Calculate the frequency of the sound heard by the person as the car approaches. The speed of sound in air is 340 meters per second. So, this is a Doppler effect question. FO equals Fs V divided by V plus or minus Vs. Now, what do these numbers mean? Well, FO is the observed frequency. So that is the sound heard by the person as the car approaches. That's the one that we want to know. Fs is the frequency emitted by the source, the frequency that the car is giving off. V is the speed of sound, 340 meters per second. Vs is the speed of the source, which is the speed of the car in this case. So I've put these numbers in. I've also selected minus in the plus or minus bit because the car is moving towards the observer. The way I always remember it is I think of the Doppler effect in terms of ambulances. You know, as an ambulance comes towards you, it goes, nino, 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 as it goes away. Nino, 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 nino. Now, if an ambulance is coming towards me, that implies I'm ill. There's something wrong. I'm injured. And that's a negative thing. So towards is negative. If the ambulance is moving away from me, it means I'm probably fine. And that's a positive thing. So moving away is positive. That's how I always remember it. Anyway, we work out the sum and we get an observed frequency of 530 hertz. Part B. This same effect is used to determine the speed of red blood cells through blood vessels. Ultrasound waves are transmitted by a probe. The frequency of the ultrasound waves changes as they reflect from the red blood cells. The probe detects the reflected waves. The relationship of the red blood cells can be determined using the following relationship. Delta F equals 2F V RBC cos theta over V, where delta F is the change in frequency, F the transmitted frequency, V RBC is the velocity of the red blood cells, V is the velocity of the ultrasound, and theta is the angle between the direction of the waves and the direction of the blood flow. So, The frequency of the ultrasound transmitted by the probe is 3.7 megahertz. The velocity of the ultrasound is 1,540 meters per second. During one test, the angle between the direction of the waves and the blood flow is 60 degrees. The change in frequency of the ultrasound is 286 hertz. Calculate the velocity of the red blood cells during this test. So, we've got this formula. We just need to stick the numbers that we have into the formula, which are these. We have to be aware that we're working out VRBCs. This is a wee bit of a tricky bit of rearranging to do. We need to move that 1,540 to the other side. So we multiply the 286 by the 1,540, leaving us with 2 times 3.7 times 10 to the power 6 times cos 60. And then we can divide across 286 times 1,540 divided by 2 times 3.7 times 10 to the power 6 times cos 60. And that gives us a velocity of 0.119 meters per second for the red blood cells. Number 6. Stars emit radiation with a range of wavelengths. The peak wavelength of the radiation depends on the surface temperature of the star. The graph shows how the energy emitted per second per unit of area varies with the wavelength lambda of the radiation for a star with a surface temperature of 5,000 Kelvin. A second star has a surface temperature of 6,000 Kelvin. On the graph above, draw a line to show how the energy emitted per second per unit of area varies with the wavelength lambda of the radiation for the second star. So there are two things that happen with greater temperature. Firstly, a higher temperature causes more energy to be emitted per second per unit of area. So the graph will peak higher, but it will also have a peak wavelength that is shorter. So we need to show a peak wavelength moved towards the left of the graph and a higher peak wavelength as well, because it's emitting more energy per second per unit of area and is also peaking at a shorter wavelength or higher frequency. Part B. The table gives the surface temperature T in Kelvin of 4 different stars and the peak wavelength lambda peak of radiation emitted from each star. Use all the data in the table to show that the relationship between the surface temperature T of a star and the peak wavelength lambda peak radiated from the star is T equals 2.9 times 10 to the power of minus 3 over lambda peak. So, if we rearrange that a little bit, we end up with T times lambda peak equals 2.9 times 10 to the power of minus 3. So that's what we want to establish is true. So for each of these sets of values, we need to multiply the temperature in Kelvin by the peak wavelength. So for the first star, we get that value. For the second star, we get that value. For the third star, we get that value. And for the fourth star, we get that value. And if we look at the values that we have there, if we round them to 1 decimal place or to 2 significant figures, we get a constant of 2.9 times 10 to the power of minus 3. And that establishes that the relationship is true. And that, folks, is all of the astronomy questions from the 2019 paper. So I hope you found this helpful, and I will talk to you again sometime soon.